let's investigate a couple of problems that involve power. So the definition of power is simply work divided by time. It's the rate at which you do work. So pretty straightforward. We can actually then say power is simply equal to whatever work we're doing. So in this first problem, right, we've mentioned this before, the athlete is pushing up on the stairs while gravity is pushing down on the athlete. They're going to work out the same, right? So we said that the work done by the athlete, we'll say A, minus the work done by gravity, that would be the change of kinetic energy, but that's simply zero. Because if you can see here, the athlete runs up at a constant velocity. So if those two, if the speed isn't changing, or velocity is not changing, then the work done by the athlete and the work done by gravity are the same. And of course, that's the easy one then. You might recall work done by gravity is mgh. So we can put that in here, mgh divided by t. For this case, let's put our numbers in. We've got a 56 kilogram athlete times g times the height. In this case, it is 3.2 meters. And we get 4.4 seconds. So go ahead and quickly, you can run through that if you want. Or you can wait for me to punch it up into my calculator. And I got 399. 399. And here's the deal. What are the units of, this is really, again, this is a joule per second, right? So joules for work in seconds. So 399 joules per second. And we can abbreviate that with a W for watt. Like that is if you have a light bulb, like a 60 watt light bulb or a 75 watt light bulb, that's the same idea. A 100 watt light bulb uses 100 joules of energy per second. It's a different kind of energy rather than gravitational energy, but there you go. So pretty straightforward. Now, one thing some athletes want to do is figure out, and we'll see this in our next problem, we'll need this. We use watts. It's a pretty common unit of power, although another one is the horsepower, especially for cars, motorcycles, etc. And 1 horsepower is about 746 watts. It's pretty hard for an athlete to generate more than 1 horsepower for an extended period of time, more than a dozen seconds, to generate more than horsepower is quite substantial. So in this case, we just divide 399 divided by 746, and that she's generating about 0.54 horsepower. That's pretty impressive. Of course, this says watts, so we put 399. Well, let's take a look at the next problem. Scroll up, here we go. Now we've got a car. So car of mass, in this case 1120, drives up a hill at a speed of 45 miles per hour. If the hill is a slope of 10.0 degrees above the horizontal, so they were saying that this is 10 degrees, this is 45 miles per hour. This is 1,120 kilograms. All right, and we want to find how much power does the engine need to generate. Well, first, notice this, right? Let's convert this to meters per second. The formulas that we're going to use are always MKS formulas. So 45 miles per hour. It's going to be about, almost exactly 20 meters per second. All right. It's 20.1, so we'll just go 20, just like that. Now, if we use our formula, power equals work divided by time, the problem is, what do we what you got here? We have a velocity, right, of now 20 meters per second. There's no velocity in that formula. Not showing, but there really is. And let me expand this out. Let's write work is really force times distance. That's the definition of work, divided by time. And then let's look at this. Distance divided by time. Well, last time I checked, distance divided by time is in fact average velocity. So we can actually express power as a function of velocity by saying it's the force times the average velocity. So this car is driving at a constant speed of 45. We'll assume that, right, to maintain that speed. Notice, so it's going to be going at 45 miles per hour, 20 meters per second. And now we need the force. Well, what force does it have to overcome? This we might remember, right? On an incline, the free body would be mg Fn, and then the friction force. Friction force is headed, or not the friction force, I'm sorry, the parallel force, right? mg sine theta. That's the force down the hill that the car has to overcome. It's going to be a function of this. You can imagine the bigger the angle, the more the force that car has to apply. So in this case, let's put all that in. The power is mg sine theta times our average velocity. We'll put our numbers in. We got 11, 20. Of course, you can play along with the home version of the game if you're checking this, working along with me, or if you're just checking how to do it. Hopefully you've done this. Sine of 10 degrees times our velocity of 20. So let me crank that out. It's going to be a relatively large number because a joule is actually a pretty, just remember this is joules per second. Joule are a relatively small unit of energy. And I got, oh boy, about 38,120 joules per second, right? Or watts. Now, 38,000, by the way, if you're dealing with, if we're ever asked about this, sometimes you might have to express this as 38,000 watts, 38,000 kilowatts. In this case, we want horsepower, so remember we're going to divide that by 746 watts per horsepower. So divide by 746, and I get, about 51 horsepower. 51 horsepower. That's not too bad. If you are familiar with cars, most cars have way more than 51 horsepower. Remember, this is to keep it, this is to get it going up the hill. We'd need additional horsepower. We'd need more horsepower, right, to speed up if we needed to pass a car. And we'd need even more horsepower, obviously, to get around the wind, right? We're not including air friction in this problem. Ignore the effects of air friction, which, by the way, are substantial. And again, the faster you go, the more air friction there is. So there we go. There's our ideas of power. I'll leave those here. You've got the formula, right? Work divided by time. Typically, just whatever you're going to do your work. In this case, it was this. But don't forget, you may need to change it up a little bit so that you can use the values that you're actually given.